Notes 2.2 are about an introduction to limits. Suppose a function f is defined for values of x near a. Then the limit as x approaches a of f of x equals L, some limit. Means we can make the values of f arbitrarily close to L by restricting x to be sufficiently close to a, but not equal to a. So we say that f is approaching this limit as x approaches a. In the three pictures provided, we have what we could call the function shown in different ways. And in the first situation here, we'll call this a. And a is the location of a point on the curve. And that is also the limit, because the function is approaching that value, capital L, on the curve as you get close to a. The second drawing has the point removed. So the point could be removed from the curve, and this limit would still be the limit of the function near a. So it's the same function, but we've removed a point. So we say that the limit still exists. The function has no value at a on the curve, but the limit still exists. The value of the function is somewhere else. And then the final picture, there's no value of the function at a, but the limit still exists. The limit of L still exists. So in the first picture, f of a actually equals L, the limit. In the second one, f of a does not equal the limit, but the limit still exists. And in the third one, f of a is not even defined, but the limit still exists. And the reason for this, the reason that the limit still exists, is that we can get arbitrarily close to a and still have the same limit, whether we're coming in from the right side or the left side. So what we like to do when we're asked to perform a limit is we have the ability to break it down into a right hand and left hand limit to examine the overall limit. So we're going to do that. I have an example here of the limit as x approaches positive 2 of x minus 2 over x squared minus 4. Now you've been taught that you could take the 2 and substitute it in for x to try and evaluate the limit that way. That's like the first option, the first strategy of limit solving. And when we do that in this case, we're going to get 0 over 0. So there's options from there. The first option is we could do algebra. Another option we will eventually have is to use L'Hopital's rule. We could do that. For now, I'm going to apply some algebra. I'm going to break x squared minus 4 down into x plus 2, x minus 2. That'll allow me to cancel x minus 2 in the numerator. So the limit I'm looking at now is the limit as x approaches positive 2 of 1 over x plus 2. So I'm going to take a look at that picture. I know since x plus 2 is in the denominator, I have a vertical asymptote at negative 2. One thing you might notice is there's a problem in my drawing. If you remember, we did some algebra a moment ago. When we canceled x minus 2 with x minus 2, that creates a hole in this graph. You see, we have to go by the original function that was provided. And in the original function, there were 2 points where the domain does not have a value, and that's at positive 2 and negative 2. So according to the original function, we have a vertical asymptote at negative 2 x equals -2, and we have a hole in the graph at x equals 2. So our limit is actually asking us to find the limit on the function as x approaches +2. So what I want to do is I want to look at this numerically as well. I have a picture here. I have an idea of what that limit would be from my picture right here. So I can tell what the limit would be by looking at the picture or looking at the simplified function here. But I'm going to go from the left and I'm going to go from the right, and I'm going to do it numerically to begin with. And so what I'm going to do, I'll just calculate on the graphing calculator the values that I'll get if I approach x equals 2 from the left. So if I start at 1.5 and then I work my way closer and closer and closer to 2, what kind of values will I get? So that's just a calculation. So on your calculator, you could plug in 1.5 into the function and you would get 0.286. If you plug in 1.9, you get 0.256. 1.99, I get 0.251. Okay, take a look at these y values. We're getting closer and closer to a particular number. Now, you might agree that when we plug in 1.999, we are very close to 2, but we're not at 2, because if we try to plug 2 in, we wouldn't get an answer. Instead, we get, rounded to 3 decimal places, we actually get 0.250. So it looks like as you approach 2 from the left, the value of the function is at 0.25, or 1/4. So that might make sense if you look at the original simplified function. Now let's approach 2 from the right side. So I'm picking values of x that are arbitrarily close to 2. This one isn't very close. The first one I pick is 2.5, but you know how to get closer to 2 now, right? 2.1 is closer to 2. What's even closer than that? 2.01. I'm just picking these arbitrarily. There's no rule that I'm following. I'm just getting closer and closer and closer to 2. And now I'll just plug those values into the calculator and see what I get. Really close to 2, and look what I get. So now I see the same value coming out no matter whether I approach from the left or I approach from the right. So if the value is the same as you come from the left and you come from the right, then that is the limit of the function at that value. So the limit as x approaches 2 of x minus 2 over x squared minus 4 is 1/4, or you could have written 0.25. Let's take another quick look at our diagram for the moment. What if the limit was to -2 instead? Look at your left-hand limit. As we approach -2 from the left, we're headed toward -infinity. As you approach -2 from the right, we're headed toward +infinity. They're not headed to the same value. So the limit as x approaches -2 of x minus 2 over x squared minus 4 does not exist. They both need to be approaching the same value. Now I want to look at this limit as x approaches 0 of sine x over x. This is a very popular function to show up in AP Calculus, so I would like to introduce you to it right away. And I would like to do that on the graphing calculator. I want to go to the y equals menu and enter in our function sine x divided by x. I'm going to hit zoom, choice 4. Choice 4 gives me a nice closer look to the origin. Okay, so this is sine x divided by x. The first observation I'd like to make is, shouldn't there be an opening here at x equals 0? Because it was sine x divided by x, and you can't divide by 0. Well, to check that, you could jump to that location on the curve by hitting trace, 0, enter. And you'll notice down at the bottom, we are at x equals 0, but there is no y value. So there is, in fact, a hole in the graph right there at x equals 0. The feature I want to look at, though, to observe that a bit closer is the table feature. Now look on this calculator above the window button. There's a table set menu, and then above the graph button is the table. So when we're ready for the table, we're going to hit second graph to get the table. Here's the table set button, so hit second window. In our case, we want to be near 0. For fun, I'm going to enter our start x value at -1. Hit enter. And then this is the intervals over which we're going to look at the table. So you know how like when you make a table and you x is 1 and x is 2 and x is 3, that's a delta table of 1 or a change of 1. I'm going to make it smaller. So I'll make it 0.2. 0.2. Let's see what the table looks like now. So I'm going to hit second graph to see what the table looks like. So this is good. When x is 0, here's the error. So we shouldn't have a value there because we're dividing by 0 in that case. Here I started the table at -1, and then you could see my x's as a change of 0.2, and I go higher. You're not restricted to this view of -1 up to +1. You can use your arrow keys to look at smaller values of x, or you could use the down arrow key to look at larger values of x. So you can move around the table. So if your table start isn't what you want it to be, you can adjust it that way. I think this table does a good job of taking one-sided limits for me. So notice how when x is going from -1, I'll move that a little bit. When x is going from -1 to 0, the values of y increase 0.84, 0.89, 0.94, 0.97, 0.99. So it's getting really close to a number. And then the same is true if we come in from the right side on a right-sided limit. We start at 1 and go down to 0. We do come up to 0.99. Now if we want to look at that closer, we could go back to table set. So second window takes us back into table set, and we can make the delta table smaller, like 0.1, and hit second graph to see the table. So now as we approach 0 from the left, you can see the values getting closer and closer to 1, 0.97, 0.98, 0.993, 0.998. These are getting closer and closer to 1. And then we could say the same on the right-sided limit. I'll scroll this down so that you can see us coming in from the right side. Coming in from the right side, the values are going 0.92, 0.94, 95, 97, 98, 99, 3, 0.998. So these are getting closer and closer to 1 as well. So since the left-hand limit as x approaches 0 is 1, and the right-hand limit as x approaches 0 is 1, then the limit on sine x over x as x approaches 0 is 1. Look at the graph one more time. We said trace 0, enter. So we could be right on that spot. But if you arrow left a little bit, you can see the same values here in the graph that we were seeing in the table. So as we move closer to 0 from the left, they get closer and closer to 1. And then the same is true when we move in from the right. You get closer and closer to 1. Example has a piecewise function, and we'll call that piecewise function f. And part A is asking me to find a one-sided limit because of this little negative after the 2. It's not in front of the 2. It's not like it's negative 2. The negative is after the 2, so that's a one-sided limit. Head toward 2 from the left. What value are you at when you get by 2? Well, you're up here, and that's 3, so the answer here is 3. Now approach 2 again. This time approach it from the right. What value would you be at if you got really, really close to 2? This time you're at a height of 1, so that limit is 1. Now we're going to put them together. If you just take the limit as x approaches 2, and you're not talking about the right hand limit and you're not talking about the left hand limit, you're saying the limit as you go to 2, the right hand limit and the left hand limit have to agree for you to have a limit. But we just did those. The left hand limit is 3 and the right hand limit is 1, and they do not agree. So this one does not exist. That limit does not exist. Is part D. What does it mean to find f of 2? Well, you want the value of the function where x equals 2. And x does not equal 2 for this piece of function right here. It equals 2 for the piece of function that starts there. So that value, f of 2, is 3. In letter E, the limit as x approaches 0, the function where x equals 0 does not have any jumps to it or holes in the graph or anything going on. It's a continuous function right there at x equals 0. So that equals the value of 3. And then f of 0 also equals 3.